All right, we are now recording. Let me set up from the current slide. I thought I was on it, but obviously not. Okay. Before we hit new material, I need to take some of these downstairs. I hope the business office is open again. They said last week, don't add or drop courses for students awarded process grant aid complete registration until further notice. They haven't notified yet, but hopefully they're finished by now. On the administrative calendar, this week is the last week for first mini-term courses, which means sometime over this coming weekend will be midterm. And classes begin for a second mini-term next Monday, 1 week from today. That also means that our midterm progress reports are due by 1 week from Wednesday. Okay, so be sure you get stuff in by then. You've already turned in a paper, so I think you're in good shape. But the others, anyone listening at home, sometime between now and next Wednesday, be sure you get it. Either your first test in, your paper in, or both. All right. Coming up on Wednesday, our volleyball team will be hosting Snead State Community College, and that game will be over on the Birmingham West Campus in the Arthur Shores Fine Arts Building, which is also our gymnasium, beginning at 6 o'clock next Wednesday, day after tomorrow. All right. That one's over with. I need to take that downstairs. Recycle. And I think I announced to you before, you're not going anywhere else, so I'm not going to read through all these scholarship summit for fall 2019. And the NASA program, I doubt if you're going to be participating in that either, but if you are, here's the information up here for that. Okay. We're in Chapter 13, Functions of Several Variables. 13.1 is Introduction to Functions of Several Variables, and they're doing all sorts of variety of things with this. And we're on Example 4 on page 876. This is sketching a contour map. And they say see larsoncalculus.com for an interactive version of this type of example. And I bet you in there they'll have the graphics out their ears for that, so you'd probably be able to see it be put together better than what I'm going to do here, okay? So what they are giving us is a hyperbolic parabola. I shouldn't have said that. I should have let you say what that was, but it's okay. I'll let it slip. And that was z, I can't write, is equal to y squared minus x squared. Now, if you hadn't caught what I said, that is a hyperbolic paraboloid. Why hyperbolic? If you look at z equals 0 or any constant, well, not 0, but any constant, if z is equal to 0, this is going to be x squared is equal to y squared, so x is equal to minus y, and y is equal to minus x. So it's going to be the two lines that cross like that. So z is equal to 0, that's right. When z is equal to a positive number, that means that y squared is greater than x squared. And that gives you a hyperbola in the xy plane, or parallel to the xy plane, when z is positive. When z is negative, it's a hyperbola where x squared is greater than y squared, and that would be reverse the orientation. One would be opening like this, and the other opening like that, so to speak. So let's just take that z positive. Okay, when z is equal to 0, the line x equal y, x equal minus y, those lines would be your two lines of intersection. When z is positive, y squared is greater than x squared, And that means in the y-axis you'd have a hyperbola open like that. Let's say if z was 1. Okay, you're 1 unit off the floor, okay? So you're up here somewhere, and in that plane you'd be a hyperbola like this and back in the fan room like that. And then you go up from there. When z is negative, say a -1, then the x squared is greater than the y squared, so your hyperbola opens like that and out toward the hospital over there. So that's what it would look like, and then as you go further up, the z is going up, and the difference between these are going up, so your vertex would be increasing as well. So if z is equal to 2, y squared is 2 more than x squared, so it would be like that. And so you have hyperbola that way. Everything parallel, except for z equals 0, everything parallel to the xy plane is a hyperbola. So that's a hyperbolic part of it. The part that's the parabolic part is cover your x. When x is 0, this is z is equal to y squared. So that's a parabola that's, let's see if this is a y plane, that would be the one that opens from the origin, opening up like this, okay? And z is equal to, if y is equal to 0, then your parabola is opening downward, okay? So that then produces what they have in the book, okay? And they have put a nice orientation on it, which would be a lot better than I could draw. Okay, there's your two lines, y is equal to minus x and y is equal to x. Okay, they go like that. They are in the xy plane. And then your parabola going up, where y is greater than x, there. Those are your your hyperbola going up, and then turn them this way, coming down, where x squared is greater than y squared. So they're opening along the x-axis. I'm about to lose my book here. Okay, your parabola going up is in the, when x is equal to 0, z is equal to y squared. It's hard to show it exactly from this angle because it curves around, but you have a parabola like that, and the ones going down are opening like this. Now, when let's see, if your x is goodness, this book is heavy. If x was either larger, positive, or negative, because you're subtracting x squared from it, you're going I can't hold it much longer. Yeah, the parabola just keep going up that way, and the others keep going. Yeah.
Let's put y equals 0.
Y is equal to 0.
Okay.
Got it.
All right. Now, that does not mean x can't be negative, just that it's back there in the wall. Is that right?
Yeah. The parabola z is equal to minus x squared. The z-axis is, of course, the vertical, and the x, so you're in the xz plane there. Okay, they're opening downward. Okay, so when y is 0, that one is at the origin going down like that. Half of it's going out into the street, and half of it's coming here. Look down on the first floor. They're opening downward. Now, when z is, or when y, when y is either positive or negative, doesn't matter, then your z is equal to x squared plus something, okay? So your parabola is still, minus x squared plus something. It's now going down, but say the y is out here at 1. Now the z is up here at 1, and it's still opening downward. And then the further out here they get, and that's what you see happening here. There's one parabola, but you see they're opening higher and higher and higher in this dimension. But when you're along the x-axis, this is with the y-axis in the middle. With the x-axis in the middle, the parabola are going down. That's when y is equal to a constant. When x is equal to a constant, then this is a parabola opening upward in the xy. And then as x gets larger, either positive or negative, they're just going further down into the first form, because those parabolae are going downward. And that's what's hard to see on here. The parabola that are doing like this are going further and further down, where these are going further and further up. This one is right at the origin, and then any past that, you're out here and you're going down like this. The next one's going down like this, so it's hard to see it from the perspective they got it here. But your parabolas are when x is plus or minus anything, this is still a negative number. So your z is equal to y squared, which would be the parabola that opens like this. This is half of it here. Then the next one will be further down because you're subtracting a number from it. And then further down, further down. As x gets larger and larger, they're going further down. And when x are getting more and more negative, that's back there, they're also going down. Because I'm doing like this, but they're getting, those parabola that open like this are going further and further down. Along this way, the ones that are upside down are coming further and further out as you go back like that. So that's why it's the saddle point there. Okay. That's doing 11.6 or whatever that was. That's what we were doing in that. What they're asking for us to do here, they show it in the figure, it says, sketch a contour map of this surface. Now, the contour map is usually traces parallel to the XY plane. Oh, I forgot to mark Josh here. Normally not having you here. No, never mind. Okay. Whoa. I keep hitting yuck. My flash drive is getting pretty fragile. It's an old one, and anything that hits it disconnects it. So I don't know what it's doing now. But I think we're okay because we're already loaded. Okay, so what we're doing now is doing our contour lines parallel to the XY plane. Now, of course, with when z is equal to 0, right on the XY plane, you have these that cross in the center there. Nothing else crosses in the center. Now, as you go down, these are becoming more and more negative going down. So, parallel or opening on the X, I think they've got this backwards, if I'm not mistaken. No, they got it right. I was looking at what they were doing. Okay. once at opening this way, your z's are getting more and more negative, opening around the x-axis, front and back. They're going more and more negative. So sure enough, this is -2, -4, -6, -8, -12, -2, 4, 6, 8, 10, and 12. And then going up this way, when you're paralleling the y-axis, they're increasing because now your contours there would be 2, 4, 6, 8, 10, and 12 just barely shows up there. And there's 2, 4, 6, 8, 10. I don't know if they show a positive 12 or not. Yeah, they do, but they don't on the graph here, but they do down here. And that's your contour lines. They're rising around the y-axis, as you go out the y-axis, and falling as you go, increases on the positive or negative on the x-axis. So, pretty symmetric looking thing here. Not at all symmetric looking as a saddle point, or not very much symmetric. And the way they suggest you do that, which is perfectly fine, is basically what we've been saying. You just let C be various values. And of course, when C is equal to 0, you get the crossing lines, okay, at the origin, okay? And then when you say Z is equal to 1, you get y squared minus x squared is equal to 1. And that's a hyperbola that's going up because the C is going up. So on the y, that's getting further and further apart. And those are positive values as you go up. And when you let z be negative, like -1, that would then be y squared minus x squared. And you could flip that around and say x squared minus y squared is equal to 1. But it's not really very fair to do that. That's your hyperbola, but the z is at -1, so I don't really like doing it that way because then I think I'm going up it again, and I'm really not. I'm actually going down. So I'm going to erase out, and that to me can be more confusing than it's worth. But what they say to do is whatever your z value is, divide by it, okay? So when z, say, is 4, you have 1 is equal to y squared over 2 squared minus x squared over 2 squared. That's the one they showed in the book, and c is equal to 4. And that looks more familiar to us to being a hyperbola, okay? And where 2 is the point on x that the vertex on x, on y, because that's the larger value. And when they're negative, it just reverses. All right. Contour lines are so much fun to draw. But let's move on to, I don't think I need this, okay. Let's move on to, that was example 3, we've already finished. Level curves, and one example of functions of two variables used in economics is the Cobb-Douglas production formula. And that function is used as a model to represent the numbers of units produced by varying amounts of labor and capital. Obviously something economists worry about. Of course, we pure mathematicians and engineers, that's so pedestrian, we don't worry about things like that. If X measures the units of labor and Y measures the units of capital, then the number of units produced is f of xy is some c, arbitrary constant here. A is also arbitrary constant. X raised to the 8th power and y to the 1 minus 8th power. Okay, 1 minus 8 power. Okay, where C and A are both constants. C and A is always between 0 and 1. Otherwise, it doesn't make a lot of sense. Okay, now the only thing I can figure out of, well, I don't know, capital is the thing that messes me up here, because I guess what you've got is a fixed budget, and you can pour the money into mechanizing if you do all Y's and you have very little labor, or pour the money into labor and don't mechanize, because you only have so much money, and if you put it into labor, you don't have it to spend on capital. If you put it into capital, you don't have to spend on labor. So that's my pedestrian interpretation of this, since I'm not a economist. And they just give you that and then don't give you example 5. I thought they had example 5 coming up, but they don't. So let's us do example 5 here. Okay. A manufacturer estimates a production function to be f of xy is equal to 100, that's the arbitrary constant c, x to the 0.6, excuse me, y to the 0.4. Remember, the exponents have to add to 1, okay? Because whatever a is, the exponent for x is, the exponent for y is 1 minus that, and they both have to be positive, okay? Where x is the units of labor, y is the number of units of capital, okay? Compare the production level when x equal 1,000 and y is equal to 500 with production level when x is equal to 2,000 and y is equal to 1,000. So no, obviously your total cost doesn't have to be constant because these are nowhere close to that. So I don't know. Yeah. X is the number of units of labor, y is the number of units of capital. Now, all you do is plug and chug here. So your f of xy, well, let's call it x of 1,500. Well, my pen. Okay. Of 1,000 for x and 500 for y, this would be 100 times 1,000 to the 0.6 times 500 to the 0.4. Okay? Pull out your calculators, chug away. Okay? And this gives you an output of what you're going to get out of that much is 75,786 units. Now y'all check it. I'm just writing down what they have in the book. Okay? And they say this is approximate because I bet you those are not perfect numbers there. They're decimal numbers for sure. But the number of outputs is functions using the number of units produced by varying amounts. Okay. The second one, f of 2,000, so you're putting 2,000 units of labor in and 1,000 units of capital. You basically doubled everything, and that would be 100 times 2,000 to the 0.6 times 1,000 to the 0.4. And they give this to be everything doubled. So this doubles too. 151,572. And that's approximate again, not exact. And isn't that just about it? That is almost exactly double, okay? The place where it falls apart, when you double 6, you get 12, so that'd be 2 carry 1. And double 8, 16, 17. Okay. And double 7, you get 15. So the last 2 digits don't seem to be an exact double, but everything else is. Okay. While the last 2 are not, they're not. The level curve for z is equal to f of xy. They say when you double both inputs, you double production, which sort of sounds like it ought to make sense. But then I'm not an economist, so I don't know if that makes sense for them or not. But here is your x is 1,500, your y, you're on right in there. When you're 2,000 and 1,000, you're right in there. So your production function is what your z is. And you can see why it's not an exact double, kind of, because the curves are not quite, but it's awfully close to being an exact double. I don't know. This part of this chapter, to me, makes it, well, later, if you tie in what we're doing here with what we're going to do later, it will make sense. But that's a big stretch. Okay. So let's move on to any questions on this. These are just sort of examples. We didn't do a bit of calculus with that at all. Okay. You just plug in numbers. Okay. So let's move next to what they call and what are level surfaces. Okay. The concept of a level curve, which you got a 3-dimensional function and you're taking the contour lines in any plane or something parallel to a plane, can be, and that's a level curve. If you extend that concept in 1 dimension, you get a level surface. And if f is a function of 3 variables and c is a constant, then the graph of the equation f of x, y, z is equal to c is a level surface of f. And we saw this before on our parabolic hyperboloid, no, elliptic paraboloids, or elliptic paraboloid of 1 sheet, the cone, and of 2 sheets. And basically you're just moving up this process here. I think, yeah, the C1 is when you've got it of 2 sheets, okay, when this C is large enough that, you know, that'll work. When that's equal to 0, so to speak, that gives you your elliptic cone, and then when it's even smaller than that, or let's just say larger than that here, it looks like that would give you your elliptic paraboloid of 2 sheets. Okay. Why they show this here? Well, they're skipping example 5. Oh, no, I'm sorry. We just did example 5. Here's example 6. Describe the level surfaces of this function. F of x, y, z is equal to 4x squared plus y squared plus z squared. Okay? Well, each level surface will then be some constant. Okay? The f is going to be a constant 4x squared plus y squared plus z squared. Now, I am having trouble seeing how their picture fits too well, because their picture they have in the book looks like spheres. This should be concentric ellipsoids, because you see you're in the XZ plane, they should be circles. Your level surfaces of what you form should be circles, but this should be an ellipsoid, because your X term has a larger coefficient. And I just don't see the connection between what I see here and what I see here in the text. Maybe I'm just not getting my perspective right on it, but it really seems like it's, however they're drawing this, they look like they're drawing. Now that I look at it, it could be the X's have been pulled in, because the YZ is basically what you're seeing, and that is a circular shape, and your X's are being squeezed in closer to each other. So I guess that could be a correct shape. But all the level surfaces are ellipsoids whose cross-section parallel to the XY plane are circles. So that's what you're seeing, the circles there, because you don't have the depth to see that there's skinny circles there. Flat circles like this, they're like this, circular this way, but elliptical that way. And so you see the dimension here is far greater than the dimension there, like 4 times as great. So again, I don't find those all that, especially matching the drawing there. It doesn't do anything for me. Here's their drawing. Each level surface, as I said, was 4x squared plus y squared plus z squared is equal to c. Equation for the level surface. So the level surfaces are ellipsoids whose cross-section are parallel to the YZ plane are all circles, and we said that already. As c increases, the radii of the circular cross-section increase according to the square root of c. Okay. And maybe that's what they did. They just drew these 3 level surfaces, 0, c equals 0, c equals 14, and c is equal to 16. All right.
Looks kind of flat.
I'm sorry.
It looks flat.
Yeah, it surely does to me too. And I guess that's what they're kind of showing here. When c is equal to 0, and let's just get it. You're absolutely right. It does look very flat, and that's why I have trouble seeing them as a level surface. Okay. Now, when c is equal to 0, you're only that point right there. I mean, it's not a very interesting problem, because x has to be 0, y is equal to 0, z has to be 0, because for c to be 0, they have no choice. That's the only way, because they're all squared and all added, so there's no way to get anything other than zeros. Okay, so the next one they do with x equal, with c is equal to 4, then you have, there's 4 out here, then divide everything by 4, and so this is a 1, 4, 4. So in that case, your x, and they don't show anything on x, but you come out 1 unit here, but then go, and x equals 0, you have the circle, kind of like the other representation better. Before you divide it by 4, then you well, it still doesn't. What I can't see is where this crosses here. It crosses at 1, where it crosses here plus or minus 2, and here plus or minus 2, but here it's only plus or minus 1. But there's no, you don't get any help to seeing that that may be a little thicker. You just focus on that point in there. That's not what you're focusing on. You have just a little bit of bulge here, okay? And then the next one, when c is equal to 16, then divide everything by 16, and this becomes 4, 16 is 16. Well, this certainly, your y and z's are 4s, twice as far. These are 2s here, these are 4s here. And again, there's nothing that, I guess the closest thing, and this is a stretch, it looks like this line is sort of fading because it's actually behind the surface. This one's a little bit brighter, but still fading because it's only one high surfaces. And this one out here, that here, there's no beyond out here. So there could be an opening this way along the x-axis. You just can't see it. It looks like it could be lighter here, so you're behind it. This circle here up to that point, and on this one you're behind it until it's somewhere around there. And that's going to bring the perspective there. But yeah, I'm really having to stretch to try to imagine that. So I don't really think it's all that useful to spend. I think we spent too much time on it now, but what they do say, these could be isothermal surfaces. I can't for the life of me figure out why the thermal gradient is so much shorter in the x direction, but even in the y and z, different specific heats in the x direction, I don't know. Okay. And then the last thing they do here is, okay, if the function represents temperature at the point x, y, z, then the level surfaces are called isotherms or isothermal surfaces. Okay? And that would be a good three-dimensional representation of what's going on if you had, say, a single flame or heat source in the middle. You'd have to have something bizarre there to make the x that much slower in advancing. Okay. Now, for the life of me, I don't know why they put the computer graphics section here. Unless you have them, it doesn't make a lot of sense, but even if you do, you just use them. And the problem of sketching a graph on the surface in space can be simplified by using a computer. Thank you very much. Although there are several types of three-dimensional graphing utilities, most of use some form of a trace analysis to give the illusion of three dimensions, even when they fail miserably. Using such a graphing utility, you usually need to enter an equation of the surface and the region in the xy plane over which that surface is to be plotted. You might also need to enter the number of traces to be taken. So here's what we got. Here's a surface. F of xy, that's your z basically in this case, is x squared plus y squared times e to the 1 minus x squared minus y squared. So you could write this x squared plus y squared e to the 1 minus x squared plus y squared. If you put this thing in parentheses after the minus sign, that would be it. You might choose the following bounds for x, y, and z. The x could be anywhere from plus or minus 3. Y could be anywhere from plus or minus 3. Z, however, because e is always positive, and these certainly are always going to be positive, this has got to be non-negative, so you'll start 0 up to 3. Okay. Now, this figure shows a computer-generated graph of that surface using 26 traces taken parallel to the xy plane. To heighten the three-dimensional effect, the program uses a hidden line routine, and that's what I find really bizarre here. I don't see the traces parallel to the xy plane. These are traces parallel to the yz plane. And where they got the xy, I mean, sure, if you did xy's, you'd have concentric circles here, here, till you got up here, and then they go back down, and you'd have to have your them labeled that these are increasing going up till you get to this one, and then decreasing as you go further out. But these are traces parallel to the YZ plane. And yet they say, so maybe that's your hidden line, I don't know. But I don't have the graphics to play with them and show them to you. That is, it begins by plotting traces in the foreground using the largest x value, and then as each new trace is plotted, the program determines whether all or only part of the next trace will be shown. The graphics of the next slide show a variety of surfaces that were plotted by a computer. If you have access to a computer drawing program, use it to reproduce these surfaces. I don't, so let's just see what we've got here. Now these are all the three the same function. F of xy is equal to 2 minus y squared plus x squared times e to the 1 minus x squared minus y squared over 4. Now this is not anything to do with the last one, okay? And all that you see them doing here is, here you have kind of an isometric thing. Your x's and y's are like this, and your z is vertical. Z's always vertical, okay? So you've got them like this, and you're looking at it from this perspective. Then you're twisting it somewhat and having the, let me see, the x, okay. My elbows are the positive here. Otherwise I can't do this very well. So the elbows are increasing in these directions. Then when we do this, the x is going this way, y is that way. Yeah, you can see some change, but that's not very major. But twist them all around till my elbows are like this, and now you've got what was up here is now going back there. And frankly, I really don't see it doing it that well either, because this seems to have some sort of funky little thing going on here. This is between the positive x and positive y axes. And you see the same thing going here. But when you twist this on back here, between the positive x and positive y, I don't see that happening. Now it seems to be over here, not where it seemed to be in these two cases. So I don't know what I don't know. So let's not spend too much time on that one because I can't just explain it, okay? Now this is a single trace here of some type of a shape, and you get a little bit of a feel for it. You get better if you do, this trace is parallel to the XZ plane. This one you've added traces parallel to the YZ plane. And here we have Corey. Perfect attendance today, way to go. Okay, we're on Chapter 13, Functions of Several Variables, 13.1, Introduction to Functions of Several Variables, and we're looking at some computer-generated graphics that I can't begin to explain to you how they did. Okay, and this just highlights the fact that you have a depression down here, a little more toward the X than toward the Y, the way it appears here, but when you add the double traces, the traces in the parallel to the YZ plane, you get a little bit more definition. The hump here, I couldn't tell whether it's right above the y-axis or where. Here it seems like it's a little this side of the y-axis. Now, this doesn't look like it could possibly be the same graph. To me. Maybe y'all can see it and I can't. But this has the max and the min, and it's hard to tell which is which, unless you have numbers with it, on the x-axis. Both of them on the x-axis. And I can see this one maybe be on the x-axis here. I can't see this one being on the x-axis. It just doesn't look like it. And this makes it even look less likely to be on the x-axis. This one could still be on the x-axis here, but it doesn't look like it is there. Unless this is, I hadn't thought of this, underneath it. But sure enough, this is the function they say they're graphing. So when x is equal to 0, then your f is 0. So that means z is 0 anytime x is 0. So anytime, x is 0 on the y-axis, I'm sorry, I'm looking at it this way. Okay, and sure enough it is. It's 0 there, 0 there, and it's 0 here. Okay, yeah. The function is 0 there. And then I get the feeling somehow I was staring at me here, but that's just me. Okay. I still don't see, it seems like there's a little twist to this that I can't justify. But I certainly can see that on the y-axis, you're right there. The graph is there. And then it gets further out there. So when you're going this way, these are increasing. No, this way they're decreasing, and this way they're increasing in z. These are your contour lines or level curves here. And this one looks okay to be above the x-axis. And I guess this one is down here. I sure wouldn't have guessed that looking at these. You just can't get enough perspective with a flat board and trying to do a three-dimensional drawing. It's enough to drive you crazy. All right. Now this is f of x, y. These are nothing to do with each other. This is f of x, y equals sine x, sine y. So coming this way, you get your sine curves this way and that way. Okay, still not completely obvious here. Here, the square root of x minus 1 over the square root of x squared plus y squared. Obviously, I have a minimum down here at when z is equal to 0. I'm sorry, not z is equal to 0. Z is a minimum when x and y are both at 0. This one, on the other hand, when x squared plus y squared is equal to 1, that's the maximum of there. I'll take their word for it. Without the computer graphics to play around with, pretty pictures. That's all I can say about them. Pretty pictures. Okay. That finishes 13.1. Okay, you can do 5 or 7. I think you can do those. And yeah, for sure. Just determine whether the equation is a function. 5 or 7, they're both at Calc Chat. Evaluating a function, that's an easier thing to do. Just plug and chug. Do any of the odds 9 through 19. They're all at Calc Chat, 9's at Calc View. Finding domain and range, we did that last time, so any of the odds 21 to 31, they're all at Calc Chat, 23's at Calc View. Now you can think about doing 33 if you'd like. It just is these functions. Play with them, do what you can, or not. That's up to you. Sketching a surface, okay, try these if you can. Any of the odds 35 to 41, they're all at Calc Chat, 37's at Calc View. And then only if you have a graphing calculator should you try, I think, unless you want to just do it, 43 and or 45. They both should be at Calc Chat. And who knows, I don't know if you go to that website, if it might not have a graphing utility tied into it, and maybe you can play around with these. I haven't been there to see. Okay, then matching 47 and 49, you're trying to match the shapes you see in 47 through 50, basically, with the contour curves that you see in A through D. And let's just take a look and see if we can figure out what any of these are. I think 47 and 49 have to be A and or C, okay? Because they're all symmetric about the origin. You see? And 47 and 50 are, and A and C are. Okay, well, actually 48 is too, but 48 is basically your saddle point. And so that has to be D. That leaves B being number 49, and surely that looks like that's the case. I can't tell what's going on the back side of that, but on the front side, it does look like it's following pretty much what they do here. So anyway, then do any of the odds 51 to 57. They're all at Calc Chat. 51's at Calc View. Do either 59 or 61. They're both at Calc Chat. And you can explore doing 63 or 65 if you want. They should be at Calc Chat. 67 should be at Calc Chat. 69 should be at Calc Chat. You can do any of the odds 71 to 75. They should all be at Calc Chat. 71's at Calc View. And here's a goodness gracious. It's called the Doyle log rule. So since it's in your book, you can write on it. Who was Doyle? How did he come up with this law, or what do you do with it? And basically, it's what the foresters use to estimate lumber yields from a log in board feet.
What's it called again?
I'm sorry?
What's it called again?
The Doyle log rule. D-O-Y-L-E-L-O-G rule. And if I were reading this without a picture, okay, and without those explanations, I would think the log meant a logarithm. But this is a forestry log, not a logarithm log. So it's a rather bizarre thing here. And there's the rule it's given. So you can play around with that if you want. It sort of looks interesting. I'll let you determine how interesting. Temperature distributions, that's number 79. Those both should be at Calc Chat. 81 is both at Calc Chat and Calc View. That's that Cobb-Douglas production formula function. And then 83 is 2, and is 85 is ideal gas law, which you run into in physics quite a bit. So you can do that if you choose. Meteorology, I bet you these are millibars, and they are. So that's, you can choose to do that one if you choose. Construction cost, 89. And then a couple of true false, 91 and 93. They all should be at Calc Chat, and take a look at those. All right, that's it for 13.1. Boy, these introductory chapters, they just get so esoteric. You play around and do stuff with them, but you don't really do any calculus or really any math, so to speak. Maybe plug a little bit. But let's get set up for the current slide. The current slide. Why isn't it sure? Oh, there it is. Okay. And that didn't do what I wanted it to. Okay. I needed to close out. Okay. Now, oh, here's the deal. It's not reading my flash drive again, I don't think. It did this in the last class. Yeah. So I think what I had to wind up doing in my last class was, I'll get out of that, and I'll see if it even no, it doesn't even recognize I got it plugged in. Now again, this is, I need to change flash drives. There we go. All right, back to Larson Calculus, Chapter 13. Now we're in 13.2. Sorry this is taking longer. Ooh, 13.2. Finally, no. Sorry. We're going to be doing limits and continuity here, which is always so much fun. A lot of blah, 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 but let's go from here. Chapter 13, functions of several variables. 13.2, limits and continuity. All right. So try to understand the definition of a neighborhood, not Mr. Rogers, but something like a neighborhood in the plane. We'll understand and use the definition of the limit of a function of two variables. Okay? We extend the concept of continuity to a function of two variables. Now these mean two independent variables. We've always had two variables. We mean functions of two independent variables. And we'll extend the concept of continuity to a function of three independent variables. Okay. So let's start with neighborhoods in the plane. Okay. Using the formula for a distance between 2 points xy and x0, y0, that would be the square root of x minus x0 squared plus y minus y0 squared. The distance between those 2 points, xy and x0, y0. Okay? Familiar stuff. You can define the delta. That is a lowercase delta. It may not look much like a delta, but that's a lowercase delta neighborhood about the point x0, y0 to be a disk centered at x0, y0 with a radius delta greater than 0. Okay? Now, and this is an open disk. What makes it an open disk, the boundary is not included. The boundary is not included. Okay? So this is a set of all xy's ordered pairs x, y such that the distance from x0, y0, because x, y are the other point, are any distance here, and they're all less than delta. This radius is delta, but that radius is not included because it has to be less than delta. So every point inside, just inside of that dotted circle, would be in the neighborhood. Those on the circle are not in the neighborhood. It's called an open disk, and that occurs when that distance is less than delta. Delta, of course, being a positive number, usually a small positive. But that formula contains the less than inequality sign. The disk is called open, which we were just saying. When it contains the less than or equal to inequality sign, then that would include the boundary. Okay? That corresponds to the use of less than or equal to define open and closed intervals. That was in one independent variables, open interval parentheses, closed interval, the less than or equal to would include the endpoints. So what we were talking about intervals before now extends to the boundary, okay, of a region. Let the region R be a set of points in the plane, point x0, y0, in R, with an interior point of R, if there exists some delta neighborhood about x0, y0 that lies entirely in R. Okay? So an interior point, no matter how near the curve you are, the boundary you are, as long as you don't touch the boundary, you can come up with some delta. It might have to be incredibly small, but some delta that you can have that completely, the delta neighborhood is completely in the interior. However, if it's on the boundary, you won't be able to do it. Anything inside the boundary, you'll be able to get a delta, maybe that radius in 10 to the minus 7th or something like that. You can still get that point to be entirely in there. Maybe so tiny you can't even see it, but it would be. But if it's on the boundary, there's no way. Because anything that goes on this side is going to be outside, not an interior point. Okay? So, that's why quite often we stick with the interior less than delta values and don't include the boundary points, because the boundary points can't be completely in the interior. They cannot possibly be. So, if every point R is an interior point, then R is an open region. A point x0, y0 is a boundary point of R if every open disk centered to x0, y0 contains points both inside and outside R, no matter how small the delta is. If R contains all its boundary points, then it is a closed region. The entire boundary is included as well. So, moving on to limit of a function of two independent variables. I wish they'd say independent. The definition of a function, limit of a function of two variables. And when they say a function of two variables, it's f of xy, okay, as opposed to just f of x, f of xy. So that's why they don't say independent. But, yeah. So let f be a function of two variables defined except possibly at x0, y0. They don't have to be at that center point, but everywhere else they have to be defined on an open disk, so that doesn't include the boundary, centered to x0, y0, and let L be a real number. That L is going to be your limit. Okay, capital L just always the limit. Then the limit as xy approaches x0, y0 of f of xy is equal to L, even though it may not be defined. F may not be defined at x0, y0 if f is a function defined except possibly at x0, y0 on an open disk, and then if that limit is equal to L if for every epsilon greater than 0, oh, that sounds familiar, doesn't it? there corresponds a delta greater than 0, such that, now here's the difference, okay? This part looks the same. The absolute value of x, f of xy minus L is less than or equal to epsilon whenever, and before, this was 0 is less than x is less than delta. That's how it used to read in one dimension. Now it's less than the distance between x and 0. x0, y0, and xy has to be less than delta. So that's where your distance formula comes in. And now that defines your limits. Okay? That's the definition of a limit. That you're guaranteed this will be within any arbitrary value epsilon. The difference between f of xy and L will be between that. Whenever you can find the delta, that the distance between x0, y0, and xy is less than that delta. So if you can find the delta small enough, you can guarantee the limit is close enough to get f of x. F of xy. Okay. Thought we were through with these, didn't you? Oh, no. Graphically, the definition of a limit of a function of two independent variables implies that for any point xy not equal to x0, y0 in the disk of radius delta, the value f of xy lies between L plus epsilon and L minus epsilon. Okay? All right. This goes back to what we had on the y-axis before and just an x-axis here. If your delta was between here, then you can guarantee your function value was plus or minus epsilon of L here. Okay, now what we're talking about, if your xy is anywhere within the radius of delta, disk of radius delta, less than that, so that's interior point here, not counting the boundary, then your L, your word, it sounds like it looks like they got these backwards here, but maybe not. It just seems like to me that this should be the one that goes to L, and this should be the one that goes either plus or minus to L. But maybe I'm just thinking backwards here. But that there is, anytime you're within this delta here, disk of radius delta, you'll come out within an epsilon here. So for any epsilon greater than 0, you can find the delta, small as it may be, such that you guarantee the difference between that will be within the epsilon values. Okay? Basically, just like an extension of before, but before we were only talking about the x-axis and delta within plus or minus of the x value here. Now we're talking about the xy plane, and you're within a radius of delta of that point. It's still guaranteed that your y values, in this case your z values, are within epsilon. So I think, okay, the definition of the limit, you know, I got my watch out to bring with me and left it right up there in my office again. I did it this morning, did it again now. The definition of the limit of a function of two variables is similar to the definition of the limit of a single variable, yet there is a critical difference. Okay? Critical difference. To determine whether a function of a single variable has a limit, you need only test the approach from two directions, from the right and from the left. Okay? And if they match, then the limit exists. When the function approaches the same limit from the right or from the left, you can conclude that this is, again, one independent variable. These two statements are. But when you're dealing with two independent variables, you can approach it anywhere in that plane. Come in a radius, circle in, weave your way in. Any way you want to do it, you must be able to show it works any way you come in. So for a function of two variables, however, the statement as xy approaches x0, y0 means that the point xy is allowed to approach x0, y0 from any direction whatsoever. If the value of that limit as x approaches x0, y0 from any direction of f of xy is not the same for all possible approaches or paths, then the limit does not exist. It may be true for some approaches. It may be true for most approaches, but if it's not true for all approaches, then the limit doesn't exist. And that does make for some problems. Okay. So here we have shown that the limit as xy approaches AB of x is going to be A. Now, I'm sure they're going to take us through some sort of runaround, but guess what? If x is approaching A here, x is going to equal A there. I mean, there's just not any way around it, unless maybe the y was, that b was 1 over A or something, and then you might have a problem. But I don't even think they can ever do that either. So if x is approaching A, the limit's going to be A. But they're going to do it a lot more. And by the way, I meant to say this while we're here. There was is a person mentioned on page 884. We've already passed it. Sonia Kovalevsky, Russian, okay, was her background, I'm pretty sure, but much of the terminology used to define limits and continuity of a function of two or three variables was introduced by the German mathematician Karl Weierstrass, okay, and his rigorous approach to limits and other topics in calculus gained him the reputation for being the father of modern analysis. So that's Weierstrass. He was a gifted teacher, and one of his best-known students was this Russian mathematician, Sonia Kovalevsky, who applied many of Weierstrass' techniques to problems in mathematical physics and became one of the first women to gain acceptance as a research mathematician. So I wanted to point that out. Two really key names there, Weierstrass, keep putting a Z in there, Weierstrass and Kovalevsky. But as you read up on either one of them, you'll find plenty of other directions you can go there. So that may give you. Now, I think I said this earlier, but let me say it again since all three of you are here. Midterm happens this coming weekend. I don't know which day, Saturday, Sunday, doesn't really matter. First mini-term ends on Friday, first mini-term begins on Monday. So midterm is somewhere in between, okay? Maybe smack dab in between, I don't know. But that means that next week, not this coming Wednesday, but the following Wednesday, we have to report midterm progress reports. Any student who does not have a passing grade at midterm, we just have to report it. Nothing comes of it. Well, hopefully someone will get in touch with a student who did get reported and see if there's anything they can do to help. But the point that I'm trying to make is I'd really like to have a score from everybody by next Wednesday. So that could be your research paper, I was just talking about, your first test. You all have them. Did you get a copy of the first test? Okay, good. So you've all got the first test. Get me something in by next Wednesday. At least one of those. Both is fine. I'll take them both. But get me something by next Wednesday. Okay, so let's see how they're going to show it, which looks obviously equal. So let f of xy equal x. Okay, yeah, that's what goes in here. And L, your limit is A. That's what goes out there. Okay? Now, according to our way of doing, for any epsilon greater than 0, there exists some delta greater than 0, such that for the absolute difference between f of x, y, and L is going to be less than epsilon whenever the delta is within the range of the delta. Okay, so here's how to say it. You need to show that for any epsilon you choose greater than 0, there exists some delta neighborhood about AB, that's what you're going around, that's your x0, y0 here, such that the absolute value of f of xy minus L, that's what I was saying, is less than or equal to that epsilon. Now, this f of xy minus L says f of xy is x, okay, and L is A, okay, then this thing is the absolute value of x minus A, as we listed at epsilon. Okay, whenever this xy is not equal to AB, lies in the neighborhood. In other words, you can exclude x equal A itself, but for any value xy not exactly equal to AB, if it lies inside of the neighborhood, that neighborhood is the delta neighborhood. They haven't gotten it all written here. I wish they had used the bottom of the page here. So that's what being in the neighborhood means, that 0 is less than the absolute value of x squared minus a squared plus y squared minus b squared. That's less than delta. Okay? Now, they've already said this back on the previous page. Exactly that, if I'm not mistaken. Right here they said it. Okay? Those two things are equal to each other. And that difference has to be less than epsilon. So those two things are equal to each other. Okay? Now, what is the meaning of absolute value of x minus a? That's actually the square root of x squared minus a squared squared. Okay? Because this is an absolute value, which is always going to be positive. So this is going to be that. Okay? Now, this is so close to what we need to be your delta. See, this is the very first part of this. So for any b, y, as long as y is anywhere close to b, it doesn't matter. Okay, so that's less than or equal to that. You just added something to it. Okay, and that thing you've added, and that thing right there is your delta. Okay, so this is equal to that by definition. And then when you add something to it, that makes this thing less than or equal to this, and that's exactly what your delta is. Now that, again, it was such a simple thing, so it's a simple solution, but it seems like it's almost meaningless. But, I mean, that really is what it takes to prove that. And, of course, if x is approaching a, then the limit is x. The limit will be x going to a. I mean, it's almost running in circles. So you can choose delta equal epsilon, and the limit is verified. Okay, for whatever epsilon, choose your delta equal to the epsilon, and then you've shown it has to be that. Okay, most of the time they will not be that direct. They just show you the very easiest one. Okay, for the example. So the limits of functions of several variables have the same properties regarding sums, differences, products, quotients as do limits of functions. So the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a product is the difference of the products. The limit of the quotients is the difference of the quotients, as long as the denominator in that quotient is not 0. Okay, for any value in that. So that's the only one that's you have to have a worry about. For some functions, it's not easy to recognize that a limit does not exist. This is not one. This one's pretty obvious. Limit doesn't exist as x or y approaches 0. Okay? It's clear that this limit, as xy approaches 0, 0, 1 over x squared plus y squared, does not exist. Because the values of f of xy, which is what this is, increase without bound as x and y get closer and closer to 0. So that limit can't possibly exist. Okay? There can't be any epsilon that you choose that as you get closer and closer, you're going to get a delta that's going to guarantee you, because as you get closer and closer, they get further and further away. So that limit does not exist. Okay? Because the closer you get to 0, 0, the more outrageously, incredibly high that value gets. So you'll never get a limit for that one. So that's one that's obviously doesn't have a limit. But what they said here, for some functions, it is easy to recognize that a limit does not exist. Okay, I misread that. Okay, I said not. Okay. Now, that was, all right. I'm sorry. I knew they had done it, but I didn't know that they had done it this quickly. Okay. Example 2, they completely skipped. Okay? So let's see if we can get example 2 to squeeze in here. How are we doing? That's not what I wanted to do. Okay. 15 minutes? Okay. Because I forgot to bring my watch in. All right. Find this limit. The limit as xy approaches 1, 2 of 5x squared y over x squared plus y squared. Okay? Now, based on what we just said before, that the limits of products and quotients and sums are exactly what you would expect. Okay? Now, with one exception, that denominator can never be 0. But as xy approaches 1, 2, that denominator will not be 0. And you're not even going to get close to 0 as long as you're within less than 1 of this. Okay? Then there's no way you can get a 0 now. So if that's the case, you can do this. So guess what you do to find the limit? Plug it in, plug it in. So what would you get?
5 times 1
times what?
2.
Okay. Over?
1 plus 4.
It's 5? So that limit looks like it's going to be 2. Okay? Yeah. Your numerator goes to 10, your denominator goes to 5, and because 5 is not equal to 0, the quotient of that is equal to 2. Oh boy, if we could get by with all of them being like that, that would be wonderful, wouldn't it? All right, let's do the next one. Okay. Big F, huh? All right. It looks like we might have room. Don't bank on it. Okay. Let's try it. Find the limit of this one. Of, oh, it looks pretty familiar, doesn't it? 5x squared y over x squared plus y squared. Have we seen that before? As xy approaches 0, 0. What you think?
First reaction is 0, but that's not right.
What's that again?
Well, my first reaction is that it's 0, but I don't think that will be.
Okay,
That's
because
simple.
because the numerator is 0, right?
Yeah.
But then you notice
And
that,
the top is 0.
well, the denominator is the bottom, yeah.
Oh,
The
yes.
denominator is also 0, okay? So this is an indeterminate form. Just like we had in 2 dimensions, it is here, I guess you call this 3 dimensions, because you have 2 independent variables and 1 dependent. Now, what we used before was L'Hopital's rule, when we had something like that. But then you're taking the derivative with respect to 1 variable. Here you have 2 independent variables, so I'm not certain you can say there is a L'Hopital rule for this, okay? So this one's a bit stranger, okay? Now, I don't think we're going to have time. What do you say we have left? About 10 minutes? Or less? About 10 minutes. What's that?
Like 8 minutes.
8 minutes. Just knowing how long these take, it doesn't take long in the book here, as it looks like, but if you're working through all the possibilities here, it is going to take longer. So let's see if we can come up with some way to approach this. Your xy is approaching 0, 0. Now, this is just a real layman's type view, okay? And this is sort of what they do in the book, too. If you didn't have that y there, I'm not sure you can say what's happening here. Still, it's a 0 over 0 case, but it's not really clear what's going on here.
We're going to do a partial similar to L'Hopital's rule, like take the partial with respect to 1 variable.
Yeah, the trouble is that we haven't done the partials yet. That's why this is a little difficult to do here, because we haven't done partial derivatives yet. You're hitting.
Is that the right trick? Do it to the partial x and let that be part of the radius of 1, and then do it with respect to the y.
Right.
And then set those both over 0
Okay.
over x plus y.
You could write the rest of the chapter almost. Yeah, you're thinking exactly like you need to be thinking, but we don't have the partials yet. Okay, because they haven't told us how to do those yet.
Except
So I
for
was-
the next class.
Yes. Well, here's the thing that I would suggest to think along. That's a binomial. I mean, this is a second order. Without the y there, that's second order. Okay, so that you could probably argue is somewhat indeterminate. But when you have this going to 0 in 3 different ways, but this only going to 0 in a sense 2 different ways, the 0 is going to win up here. So that's a really slack way of looking at it, but that will give you a limit as the limit will be 0. Now, they take you through this in the book. That, and this is sort of what I was saying, if you just do this part, x squared over x squared plus y squared, okay, and you think in terms of kind of like L'Hopital, that would have a limit of 1, okay, because, yeah,
Way bigger.
yeah, the ratio here is 1, and the ratio here would be, really wouldn't matter what it sort of does matter what it is, but this has a limit of 1, not 0, but 1. And you do it by taking derivatives of this, sort of ignoring this one, but then if you took derivatives with respect to y, that would be a 0 up here. So you'd be okay whichever way you went. You wouldn't be exploding. So the 1 wins. Okay. Then when you put this other, now the 5 is immaterial. Okay. But put the y in there and let that go to 0. Even if this limit is 1, that's still going to drag it to 0 because it, the y going to 0, in addition to 2x's going to 0, that's going to pull it to 0 faster than this could possibly. So faster is a sort of a key word there. So that's kind of what they're doing here. And where the 5 comes into play then, and this is just so quick and dirty, it's probably not very fair, since that limit is 1, here's, and this is the thing that kind of gets me. How they start this is absolute value of y is less than or equal to the square root of x squared plus y squared. Now that's the same sort of trick they used before, because the absolute value of y is the square root of y squared, right? That is absolute value of y, okay? So add something to this, and then you have something greater than or equal to that. So that's where they start this process. Again, that seems to be a favorite trick, because this is what you want this is what you want your delta to be between. So if you can keep the delta between this, that gives you a head start. So then in a sense, that gets your y being the telltale, the feature that's going to make this limit exist. Okay? So again, it's sort of a trick, okay. Anyway, we're probably just about out, aren't we?
Yeah.
A couple of minutes. So I don't think there's, see, that next slide was one that you can tell is definitely not going to 0. But that was, they jumped to that, and I miss seeing that they skipped examples 2 and 3. And for me, their figure doesn't help at all. Okay. Here, I can't tell what's going to where, and this is supposed to be the graph of it, and I can't tell you what's happening as it's getting closer to 0. Looks like it could be anywhere in here, but it really isn't. It is going to 0. So again, even the graphics aren't helpful here, or at least in my mind. I can't see it in that. But I guess what it means is they are coming in from several directions in towards 0. And that's what you've got to be able to prove. So,
we got a Z-plane over there.
What's that?
We got a Z-plane. Yes, that would be the C.
Yeah. And I mean, if it was a saddle point, yeah, I could see that would be limiting there. But this seems to have things all around it, and it doesn't look like it's telling you anything, but indeed it is. Let's see what is next. They didn't give us that. No, okay. That was just at the top. Example 4 will then be the next one we do, and that's a limit like this one that doesn't exist, but it's not, just looking at it, it's not entirely sure why it doesn't exist. So we'll start next time with example 4. And again, this is the worst part of partial derivatives, okay? once you start doing them, they really become easy. These limits, and we haven't even gotten quite to continuity yet, but when we do, well, continuity isn't so bad, but except it deals with limits. Okay, homework exercises here. Try doing 3 or 5. They're both a Calc Chat. 5's a Calc View. Try doing 7 or 9. They're both a Calc Chat. They should, I think, should be fairly easy. And then you can try doing any of the odds 11 through 24. And most of these, I think, are fairly straightforward. They're all a Calc Chat. 15's a Calc View. But the ones that get a little hairier, no, most of these are fairly easy too, but you might get some that get to be, yeah, some of these will get to be a little worse, and that would be 25 to 35. So they're all at Calc Chat, 27's at Calc View. And we'll pick up the rest of those next time. Okay. So we'll begin with example 4 next time. Again, it's pretty vague and it's harder to see in 3 dimension than it even was in 2. So we'll go from there. All right. Let's call it quits.